Here's an example that has an unusual power of e, and I don't think we've done one of these before, so let me just take a second to talk about how to find the antiderivative of this. So let's first just consider the antiderivative question. In other words, I won't worry about the 6 and the negative 5 yet, so I'm just worrying about finding my capital F, which is just the antiderivative. You might guess that because the derivative of e to the x is e to the x, then maybe the antiderivative of this guy is just itself. But remember, when one takes the derivative of something like this, the chain rule actually makes us get the exact same thing again, but then times the derivative of the power. And so in this case, that's times negative 0.05. That's the derivative of the power. The derivative of negative 0.05x is negative 0.05. So what that means is when I take the derivative of e to the minus, or e to the something times x, I get an extra number that pops out of it. I get exactly the same expression, but then times another number. So if I take the lesson that I learned from the power rule and apply it here, I can say that I should get e to the negative 0.05x as my antiderivative, but I know that's wrong because when I take the derivative, an extra negative 0.05 is going to pop out. So I do the same thing that I did for the power rule. I put the reciprocal of that number that's going to pop out in front. So this guy will have the correct derivative. If I take the derivative of this, the 1 over negative 0.05 will just sit there. The derivative of e to the minus 0.5x is the thing that I wrote up here. And so you can see that this number that I underlined twice is going to get multiplied by the reciprocal and go away entirely. And all I'm going to be left with is e to the negative 0.05x. So this thing here is the correct antiderivative. And if I were just doing an antiderivative problem, I would do that plus c, maybe simplify that. That's really just negative 200 if you do it on your calculator. So simplifying it makes it look a little better. In this problem, it's a definite integral, so I need to take my antiderivative and I need to figure out f of 6 and f of negative 5 and then subtract the two. In this case, it tells me that I can use something rounded to 3 decimal places, so that actually makes it easier. I can just plug 6 in for x into this thing in the box. Give yourself 4 decimal places for both of these, and then when you subtract them, it should be good to 3 decimal places. This question has to do with numerical integration, which is something that you can do using either applets on the computer or on your calculator. So I'll show you both ways of doing it. The applet method can use the applet that I had open before, which apparently I've closed. So in custom contents applets, there is something that says Riemann sums. That's technically the name for these sums of rectangles. So if you open that, you can put any function you want in here. So like x times log of x is the problem here. So I can put x times log of x. You do have to put the time symbol in for this applet. Of course, you can always look at other applets. We want to just hit enter, and we start to get an estimate for this area. Now, I don't have this set up right to be the integral that they gave me. Let me go back to the problem. They wanted me to have the interval 2.1 to 3.2. So back here to my applet, I have 2.1 to 3.2. And so this shows me what the region looks like. It's above the x-axis. That's nice. And this tells me approximately the value. Now, I wouldn't use this answer because they do want the answer accurate to 3 decimal places, and this is just a real rough estimate using 10 rectangles. If you want to get the very best estimate you can from this applet, turn on middle sum. That's the version that will give you the best answer, and then crank the number of subintervals up as high as it will go, which looks like 80. So you can see it really fills in the box well, but if you use middle sum and 80 rectangles, then you get 2.862 to 3 decimal places. And that ought to be a decent estimate. If you don't want to use the applet, the better way to do it is to use your calculator, because the calculator is something that you can have with you. Obviously, the applet is something you can only use while you're on the internet. So I'm going to show you next how to get the same kind of answer using the functions on a regular TI-84 calculator. So here's the screen of my calculator going to my y equals menu and typing in the function x times log of x. I have my window set. I have my window here set from -5 to 5 instead of -10 to 10 as my standard window would be in both the x and the y direction, and that gives me a little bit better picture of the graph. Now, the calculator will estimate this integral for us using a command on the calc menu. This is the same menu we used before to estimate the derivative. So calc is in little letters above the trace button on your calculator, so it's second trace, get you to the calc menu, and you can see down number 7 on this list is an integral. It looks like an integral symbol. So if we choose that, hitting enter, then I can set the lower limit and upper limit for my integral. The lower limit and upper limit are these numbers on the integral. So the lower limit is 2.1, the upper limit is 3.2. So I'll just say 2.1 and hit enter, and then it asks me for the upper limit, which is 3.2. I hit enter, and you see that on your calculator, you get a picture of the shaded region that we were looking at before. And down below it tells you the approximate area. Notice that does agree with our 2.862 that we got with the applet to 3 decimal places. So the calculator is able to do a definite integral problem. This is very useful because even on the test where I'm going to ask you to do these definite integral problems using the fundamental theorem of calculus, in other words, showing that you know how to find the antiderivative and how to get the answer, it's very useful that your calculator can check any answer that you got. So it's a good idea on the test questions to check your answer using your calculator, even if you use the fundamental theorem of calculus to find your answer. The last problem that we have is one, again, that uses a cost function. In this case, we have some research that has told us a marginal cost function. And we want to know what's going to happen if we increase production level from 450 bytes to 720. So to do this, we need to know what the practical application is for the fundamental theorem of calculus. So I'll just say this in terms of cost, but it will apply to cost or revenue or anything that we know, an application using the rate of change. So, so the net change in cost is going to be the integral of the marginal cost. And when I say net change in cost, I mean how much the cost changes from one production level to another. So net change from x equals A to x equals B. If I have two production levels in mind, then the net change in cost between those two production levels is just the integral that runs from A to B. So in this case, the integral should be from a 450 byte production level to a 720 byte production level, and I'm integrating the marginal cost function, which is 300 minus x over 3, and I don't like x over 3, I'll just write that as 1/3 x, because that's what I would want to do anyway as my rewrite. So in this application problem, the answer to the question is really just the integral from 450 to 720 of the marginal cost function. And so that's easy enough to do using the methods that we had before. The key thing here is this, this interpretation of the fundamental theorem of calculus inside of application problems. This will also work obviously for revenue and profit function, but remember we have other examples as well. For example, if we have a position function, a function that measures position, then we know that the derivative is velocity. So this is telling us that if we integrate the velocity function, we'll get a net change in position. So it's a useful general tool for interpreting the fundamental theorem of calculus in an application context.